Hello everyone, this is Oshini from Chinta.com. So today we will learn very clearly what is the true meaning of probability. I see many of my students running here and there, multiplying numbers, adding numbers, without having a clear idea about what's happening. So I'll use this video to, talk to you about that. And we will do all of that using a very beautiful problem. The problem says that a man is known to speak the truth. He is known to speak the truth 4 out of 5 times. He throws a die and reports that it is 4. So he throws a die and reports that 4 has appeared. Okay. The question says, find the probability that it's actually 4. Now, there is a bit of history to this problem. One of my friends asked this question to me, and apparently, there are many sources in the internet which solve this question in a wrong way. In fact, they get the answer 4 over 9. So, I looked into the solutions that they gave, and there was a very fatal error in those solutions. There is one place they gave a correct answer, which is in Math Stack Exchange, but they use some complicated notation for probability. Of course, Math Stack Exchange is very reliable. There is one other place where also a similar solution is discussed. So apart from those two places, all other places had the wrong solution. The wrong solution is 4 by 9, by the way. So let's see what is probability and how we can solve this particular problem. So believe it or not, probability is just a function. Okay, so what is a function? A function is an input-output machine. So maybe you are familiar with some of them. Let's say the squaring function. Okay, so it takes input as numbers, real numbers, and produces output as also numbers. I will give you examples. So for example, if the input is 3, the output is 9. If the input is 5, the output is 25. So it's just squaring the input number. The inputs are numbers, the outputs are also numbers. Probability is a type of function where the inputs are actually sets. They are sets, and the outputs are again numbers. In fact, in the case of probability, these numbers, the output numbers, are always between 0 and 1. That's how this function is designed. Now, you already are familiar with certain functions like this. Functions which take input as sets and give output as numbers. I'll give you one example. There is this area function. Area function. So if let's suppose I take the xy coordinate plane and I take this square whose side lengths are 2. So basically I am giving the input as this square shaped region. Now the output is area is 4. The output area is 4. So again, it's a function. Area is a function which takes input as the square and produces output as the number 4. Now if you take the input as a circular region, you also have a formula to compute the area of that. It's pi times whatever the radius is, r squared. So you are already familiar with functions which take input as regions or set of points and produces output as numbers. Maybe you just didn't think about these functions as functions. Like you did not think about area as a function, but it's good to start thinking about it like that. In fact, you can have more weird areas like this, enclosed regions, and you could always you could not, let's not use the word always. You could, in most cases, in most reasonable situations, you can find the area. Sometimes it's really hard, but in many cases you can very easily do it using calculus. Okay, so area is an example of a function which takes in input as a set of points and produces output as a number. Similarly, probability takes input as a set, whatever the set is, I'll talk about that, and gives output as a number. Okay, so that's what probability is. There is nothing to do with chance. Those are kind of vague. It's a function, takes it input as a set and produces the output as a number. Okay, so there are certain words that people use to describe this sort of functions. These are called set functions. In the world of probability, there are certain sets and subsets which are always associated with the problem. The first set to think about is the sample space. This is just a set, nothing else. It's just a set. So I'll give you one example. Suppose you have two coins, you are tossing them, then the sample space is this set of outcomes of that experiment. So what could be the outcomes? So the outcomes could be HH, right? Both of the outcomes are heads. It could be HT. One of the outcome is head, one of the outcome is tails, and it could be TT, right? So you are simultaneously tossing the coins. Head tails, and tail. Of course, if you do the experiment a little differently, if you first coin one of the coins, toss one of the coins, and second you toss another coin, then if you want to keep record of what happened first and what happened next, then your sample space will change. HH, HT, TH, TT. There will be 4 elements in the sample space. But if you toss the 2 coins simultaneously, then you have only 3 types of things, 3 types of possibilities, 3 types of outcomes. And this set is known as the sample space. Remember, probability is a set function. You have to input sets and you have to get output as numbers. So we are now building those sets which we will provide as inputs to our function machine, the probability machine. What is an event? An event is just a subset of sample space. A subset of the sample space. Sometimes the sample space is denoted by omega. So I'll give you an example of an event. An event, one outcome, at least one outcome is heads in that problem that we are like giving as a sample. This is just a subset of the sample space. What is it? Well, it is simply this event E, let's call it E, is just a subset HH and HT. Both of these outcomes have at least one output as heads. So what is a sample space? It's a set of all possible outcomes. What is an event? It's a subset of the sample space with some given conditions. So here I just described what are the conditions. and this is the explicit meaning of it. Okay, so now we have something called set function. What we are going to do, we are going to assign numbers. So we are going to put in events as inputs. Remember, events are sets. They are subsets of the omega, the main set, the sample space. So we are going to input events and get output as numbers. Input as events, get output as numbers, right? So there are certain conditions. So let's talk about them. So probability is a set function. It means that it takes input as sets, which are, by the way, also known as events. They are subsets of sample space. Remember, the entire sample space omega is a subset of itself, right? So that's we will come to that in a moment. So inputs as sets and output as numbers between 0 and 1. Between 0 and 1. So there are certain conditions that this function must satisfy. These conditions are: if you input the entire sample space, then the output is 1. If you input the null space, then the null set, that's also an event, that nothing happened event. This p of that is 0. And most importantly, there is this concept of countable additivity. What it means is that if you have a bunch of subsets, okay, and there are infinitely many of them, suppose there could be infinitely many, there could be finitely many as well. There is a notion of countable infinity and uncountable infinity. So I'm not going into that in great detail in this particular video. Maybe in some other video I'll talk about it. What it says is, if you want to calculate P of the union, countable union, by the way, of these sets, these are all events, by the way, events means subsets, right? Subsets of the sample space, and these are all disjoint. Events. Disjoint means the two subsets have nothing in common. Then this is equal to, so you can just individually add them up. You can calculate each of the outputs and you can individually add them up. Okay, so this is what the set function is doing. It's taking the entire set and giving us output 1. It is taking the null set and giving us output 0. And it satisfies the countably additive property. That if you have a bunch of disjoint, by the way, these are all disjoint. I told you this once. Disjoint means they do not have any overlaps. They are subsets, right? They do not have any overlaps. So if you have if you want to calculate what is the output when the input is the union of all of them, then you can individually compute each one. So you can compute P of A1, whatever the output is for, and the input is A1, P of A2, P of A3, and so on. You're going to add them up. Okay. So that is what countable additivity means. Any function that satisfies these properties. So any function P with above properties is known as a probability function. Or just a probability measure sometimes, or just probability. So if you do not understand anything from this video, just understand this, that probability is a function which when takes in sets gives out numbers in a certain way. We don't know what way, it depends on problem to problem, but this is what's basically happening. There is nothing related to chance or whatever, like those are vague words. There is nothing probable about probability. It's just a function, okay? So it takes in inputs as sets and gives that out as output as function as numbers, and it has this countable additivity property. It's a very important property. That's what distinguishes P from other set functions. Okay. All right. So now, in the context of our problem, the man is speaking the truth 4 out of 5 times. He throws a die and reports 4. So you have to first build the sample space. The sample space. Let's build all possible outcomes. All possible outcomes. Okay. So what are the outcomes? The outcomes are, well, there are two things happening. He is rolling the dice. So whatever the actual outcome is, and he is saying something. He's saying something, the dice gives some number as output, and he's actually reporting something. So two things are happening. So every sample event, every point event, every outcome, these two things are happening. So maybe he rolls 1 and reports 1. In this case, he is speaking the truth. He rolls the dice, it gives him 1, and he reports 1. Okay, so that's one point in the sample space, one of the elements in the set called the sample space. Sample space is just a set, it has many elements. This is one element. We will try to write down all the elements. Okay, so what are all the elements? Well, as I said, rolls 1, reports 1. That's one element. Rolls 1, reports 2. And then I can just copy this and paste it here. So we have rolls 1, reports 3. Rolls 1, reports 4. Rolls 1, reports 5. And rolls 1, reports 6. That's first set. It's like one part of it. What else can happen? Okay, I'll just copy this entire thing and paste it here, and maybe change the color to blue. So in this case, instead of 1, he actually rolls 2. So actually he's rolling 2, but here he is reporting 1, he's reporting 2. So here he is saying the truth. 3, 4, 5, 6. Okay, that's great. So now we know exactly what's going on. We can actually write down the entire sample space, and we will do that actually. So we can simply make copies of this, paste it here, yeah. Okay, so he has rolls 3, reports whatever, rolls 4 and reports whatever, like the 6 possibilities, rolls 5 and rolls 6. Okay, so this is the entire this entire set. Okay, so maybe I can just draw a curly bracket. This is my sample space. Okay, this is my sample space. So what I'm going to do is I will assign probability, that is, I will take events from each of the, like, singleton events. Singleton events means I'll take a subset which contains only one element of the sample space. Singleton events, I'll take singleton events and think about what is the output if I plug that set inside my probability machine. Okay, so I have this probability machine, it's a function. If I just input roles 1, speaks 1, let's say reports 1, reports 1. If I input the set of this singleton element, so this is just a singleton element, the set of this singleton element, then what is the output number? Let's think about that. Okay, so what you're going to do is every chunk, so to get all together this entire sample space omega, all together probability of omega is 1, right? We know that by the property of this function, if I input the entire space, the probability is 1. So, and all of these are disjoint, like these singleton events are disjoint. These singleton events are disjoint. So all 36 of them, if I just take 36 of them separately, they should add up to 1. They should add up to 1. So if all of them are equally probable, the meaning of it is that to each of those singletons, I assign the same value x. So if I add 36 of those x's, I should get 1. So each of them is 1 by 36, right? If each of them is equally probable, which is not in this case, we'll see in a moment. Equally probable means, and this you will see in many problems, equally probable means the singleton events means the subset of the sample space which contains one element of the sample space. The singleton events, the number, the output of that is equal, the same number for every singleton event. That's what it means to say equally probable. In this case, it's not. Okay, the point is that though all 36 of them are not equally probable, each chunk of 6 should add up to 1/6. I mean, I will be sort of, okay, so this one will be some number x, this one will be some number x2, suppose this one will be some number x3, output is some number, right? X5, x6. So all 6 of them, if I add them up, that should be 1/6. Why is that? Because the die, the problem doesn't say anything about the die. The die is a fair die. That therefore chances of falling 1 is 1/6, chances of falling 2 is 1/6, and so on. It's a fair die. So if I just focus on the 1, the number 1, all the time it is 1, they should together give up 1/6. Similarly, all the times it's 2, they should together give up 1/6. That's what the meaning of fair die is. You just focus on rolling 1, that's an event. You focus on rolling 1, that's an event. The probability of that is 1/6. Fair die means all 6 of them has the same probability. That means you assign the same number, which adds up to 1, by the way. So 1/6 each of them. So each chunk is 1/6. Okay. So now let's figure out what is x1, what is x2, what is x3, and so on and so forth. Okay. So we know that the chances of, so the question says that speaks the truth 4 out of 5 times. So speaking the truth, what this problem says, that has a probability of 4 by 5. So what I'm going to do is, I know that this is together 1/6, all of them. 4 by 5 and 1 by 5 together make 1. Speaking the truth, I'm lying. So we should be distributing these 6 events, singleton events, by these numbers 4/5 and 1/5, so that together it's either lying or saying the truth, right? It's together 1. So how are you going to do that? Well, we are going to put 4/5 to the first one because it's saying the truth, and distribute the 1/5 in the 5 others. So 1 by 5 times 1 by 5, 1 by 5 times 1 by 5. So we have to distribute 1/5 into 5 parts. So the only way we can do it is, and they are all equally probable. So so we get 1 by 25. Think how we just did it. This is a very, very important point. The probability of lying is 1/5. That happens in 5 different ways. So rolls 1 reports 2, rolls 1 reports 3, rolls 1 reports 4, and so on. So that 1/5 probability of lying is distributed into 5 equal cases. So you split it into 1/5 again. You divide it by 5. So you get 1/5 times 1/5. So it gets 1 by 25. Okay. So now we are ready to talk about this singleton case. Okay. So if I rolls 1 reports 1, this is 1/6 times 4/5. That's the output. That's the output. 1/6 times 4/5. Right? The only goal, okay, so be very careful what's happening here. The only goal is to assign numbers to each of those events, singleton events. Assign numbers to each of those singleton events such that they add up to 1. And you have to do it judiciously. So each block should add up to 1/6. This one has a 4 by 5 weight because 4/5 of the time he speaks the truth, and this 5 together has 1/5 of the weight. So together these two pieces make up 1/6. There is nothing confusing going on here. You are splitting 1/6 into 4/5 and 1/5. Splitting 1/6 into 4/5 and 1/5. That's what's going on. 4/5 times 1/6, that's one part. That's the first one. And all the 5 remaining ones should be 1/5 of 1/6 together. So each of them should be a fifth of 1/5 of 1/6. A fifth of 1/5 of 1/6. So that they together become 1/5 of 1/6. Okay. So if I take the input rolls 1 reports 2, the output is 1/5 of 1/5 of 1/6. Together 5 of them should add up to 1/5 of 1/6. So each of them should be 1/5 of 1/6 or 1/5 of 1/6, right? Okay, so we are making progress. We understand how the singletons work. How the what would be the output of the singletons? Now we really want to know what happens in this particular case. We want to know that if he reports 4 and the probability that it's actually 4. That's the case what we want. That's the case we want. So what fraction of the cases, what fraction of the probability? So here it is. Here is the fraction. He reports for, and the thing that we want is he reports for, he gets for and reports for. Okay, so let's see what are the cases where he reports for, what are the probabilities of the cases where he reports for. So that's when he rolls 3 and rolls 3 and reports 4, rolls 1 and reports 4, rolls 2 and reports 4, rolls 4 and reports 4, rolls 5 and reports 4, rolls 6 and reports 4. These are the cases. These are all the cases where he reports 4. Okay. So one of them has the probability 4/5 of 1/6, just like this one, rolls 1 and reports 1. That's the same thing here. And all the remaining ones, he has probability 1/5 of 1/5 of 1/6. It's the same thing. It's the same thing. Okay. So 5 of them has 1/5 of 1/5 of 1/6, and one of them has 4/5 of 1/6. So all the cases 1/5 of 1/5 of 1/6, we have 5 of them, and 4/5 of 1/6, we have one of them. That's the denominator. That's all the cases. All the cases where he reports for. And what about he gets for and reports for? Well, that's only one case. That's this one. 4/5 of 1/6. So let's write it there. 4/5 of 1/6. He gets for and reports for. So that's the final answer. 4/5 of 1/6 divided by 5 times 1/5 of 1/5 of 1/6 plus 4/5 of 1/6. Okay, so you can easily check that the answer is coming out to be 4/5, which is, by the way, his probability of speaking the truth. It's very nice. And if you understood how I computed the probabilities for the singletons, then you probably learned a lot about the basics of probability theory. Remember, when we say equally probable, what it really means is you are assigning the output of all the singleton events are the same and they add up to 1. And when you are looking at a particular event, let's say in this case it was reporting 4, then that's your entire world. So you take up all the singletons where reporting 4 happens. That's your 100%. That's everything. So you add them up and you divide by that, by the actual case where it's whatever is favorable to you. Reports 4 and gets 4, and reports 4. That one is favorable to you. That's what you want. That one case you want. Whatever the probability is, that you want to know as a percentage, as a fraction, how much is that of the entire cases, of all the cases where he reported 4. What I just slipped in there is sometimes known as conditional probability. I'm not going to do it in more detail than this because I always want to think in a very fundamental level at what's going on and go from there. Okay, I hope you learned something from this video, and I hope you can solve similar problems in probability theory. This is very exciting, and we will see you in the next video. Thank you for watching. Take care.